Discover Geography, Lesson 2-3, Symbology. Symbology refers to how we represent information on a map. In this lesson, we're going to look at two common types of symbology that you'll see on many maps, Isoline and Choropleth. An isoline map can be recognized by a series of concentric rings formed by lines on the map. Each line connects points with equal value for some variable that we're trying to map. So in this case, the variable we're mapping is elevation. And so each of the lines on this map connects all of the points of the same elevation. If you were to walk along one of these lines, you would not go up or down the hill. You would stay at exactly the same elevation. If you walk so that you were to cross several of these lines, then your elevation would change. You would go up or down. Here's another example of an isoline map. In this case, the lines are connecting points with the same atmospheric pressure. So if you were to travel along one of those lines that you see on the map on the day that this map was created, the atmospheric pressure would stay exactly the same all the way along that line. If you were to travel crossing several of those lines, then the atmospheric pressure would change as you went across those lines. Sometimes you'll see an isoline map in which instead of labeling the lines, they color in the spaces in between the lines. But that's essentially the same thing. So on this map showing radiation from the Chernobyl nuclear disaster, you can see that the darkest red color represents a dose from 100 down to 40, and then the next darkest red, it represents doses between 40 and 20, which means that the line that separates those two colors is the line at which you'd get a dosage of 40, which in this case is 40 times the normal exposure rate to radiation. So you can kind of translate one of these colored in areas isoline maps into a standard isoline map or vice versa. It's just a matter of what is the easiest way to represent that, the most visually appealing way to do that on the map. They're both equivalently doing the same thing. So let's take a look at a contour map. So contour lines are isolines that represent elevation. So you'll see these on topographic maps, maps that aim to show the shape of the land, where are there hills, where are there valleys, etc. To read a typical topographic map, the first thing you want to look for are what are called the index contours. These are the contour lines that are usually a little thicker and heavier than the others, and in most cases they'll be labeled. So you can see there on the map the red arrows pointing to the 100 feet, 200 feet, and 300 feet contours that you can see on this bit of map. Once you've identified the index contours, you can then calculate the index contour interval. This is the difference in elevation between two adjacent index contours. This is the amount that you'd go up or down if you traveled from a spot on one index contour to a spot on the next index contour. And so to do that, all you have to do is subtract. So you find two that are next to each other, that have no other index contours in between them as you go from one to the other. So you can see there that little bracket showing the 300 feet index contour and the 200 feet index contour. There's no other index contours between them. And so then you just subtract 300 minus 200. So the index contour interval for this map is 100 feet. Then you can figure out the interval between the regular contour lines. Those are the lighter ones, usually not labeled with a specific value. And to do that, you just divide. So if you look at that spot where you calculated your index contour interval, then you count how many steps it is along the regular contour lines to get from one index contour to the next. So on this map, you can see you make 5 steps going from one contour to the next to get from one index contour to the other. So 100 feet index contour interval divided by 5 steps that you make shows that our regular contour interval is 20 feet. So that smaller bracket there that's showing the distance between two regular contour intervals, that's a 20-foot difference in elevation. Once you've calculated these two contour intervals, then you can easily find the height of any spot on the map. So if we wanted to find out the height of the top of Schoolhouse Hill here, we'd start with the nearest index contour. So that's 300 feet. And then we would count up. And so we'd go 1, 2, 3, 4 steps. So that gets us to 380 feet, 300 plus 20 plus 20 plus 20 plus 20. And so then we know the top of that hill is going to be somewhere above 380 because it's not right on that contour line. The hill continues to go up from that, but it's somewhere less than 400 feet because we don't get another contour line that would be there if the hill went all the way up to 400 feet. So the top of that hill is somewhere between 380 and 400 feet above sea level. Any point that is on a contour line on the map, we can find out its elevation exactly. That's the elevation of that contour line. Any point that's in between two lines, we can at best find a range. It's somewhere in between the height of the contour line below it and the contour line above it, or the contour line that would be above it if the hill kept going up, or would be below it if the hill kept going down. The other thing that we can look at on a topographic map is we can see where slopes are steep and where slopes are shallow. So if you look at the river or the little stream that runs down the left-hand side of that map, you can see near the top of the map, the contour lines around that stream are really widely spaced out. Whereas closer to the bottom of the map, you can see the contour lines are much closer together right next to that stream. When the contour lines are spaced out, what that means is, as you travel horizontally across the landscape, you're not going to be going up or down very much. You're going to cross only a few contour lines. So that indicates a fairly shallow slope. Where the contour lines are close together, you could travel the same horizontal distance, you'll cross a lot more contour lines, and so therefore your elevation will change a lot more. So that's a much steeper slope. You're changing a lot more elevation over the same horizontal distance. So anywhere you see contour lines closely spaced together, that's a steep slope, a rapid change in elevation. Where you see contour lines widely spaced apart, that is a slow change in elevation. That's a gentle slope. Our other type of symbology that we want to talk about in this lesson is choropleth maps. A choropleth map is a map that's divided into area units, each of which is colored in based on its value for some variable. So in this case, the area units are counties within the United States, and the variable is the number of UFO sightings per 100,000 people. So you can see there's a different color for each county depending on the number of UFO sightings per 100,000 people that occurred within that county according to whatever data this is based on. And you'll notice that because these different levels of that variable are in a numerical sequence, it goes from low to medium to high, the colors also go in a reasonable sequence from yellow through orange to red. And that makes this choropleth map easy to read. We can look at it, and wherever we see the lighter yellower areas, we know that's less UFO sightings. Wherever we see the darker or redder areas, that's more UFO sightings. So this is a pretty well done choropleth map. So your choices in what area units you use and how you color them in matter quite a bit. So let's take a look at some maps of the 2008 US presidential election. The first map we've got here is the one that you may have seen all over the news if you paid attention during the election. You would have seen a similar sort of map, a few of the states different from the 2012 election. In this case, our area units are the states, and the colors are just two. Red if that state was won by the Republican, John McCain. Blue if that state was won by the Democrat, Barack Obama. We could also break that down, because if we look at some of those states, we could say Pennsylvania, for example. It's colored in blue on the first map, but if you know anything about Pennsylvania, you know that Barack Obama was not uniformly popular across the whole state, even during the 2008 election when he was kind of at the height of some of his popularity. There were large areas of the state, some of the rural areas through the central part of the state, where very few people were voting for Obama. Most of his votes were coming from certain parts of the state. So we could make the area units smaller. We could break it down to the county level, and so that's what that second map does. And so you can see there within the blue states, you've got lots of red counties. Within some of the red states, you've got blue counties. So it gives us more geographical detail. But that still only uses two colors. You're either a McCain County or an Obama County. So a county that McCain won by 1 vote is colored in the same color as a county that McCain won by thousands of votes. And it's a different color from a county that Obama won by only 1 vote, even though the difference between 1 vote McCain victory and 1 vote Obama victory is pretty narrow. And really those states there, or excuse me, those counties, their political inclinations are pretty similar. It's just a matter of, having 1 or 2 extra votes going a different way. So we could get into more detail with the colors. We could color them in various shades of purple. So a county is now pure blue if Obama won all of the votes, pure red if McCain won all of the votes, and then various shades of purple, more reddish purple versus more bluish purple, depending on the exact vote count in between. So now on this map, you can see there's still some areas like the Great Plains are a little redder, other areas like the Northeast are still a little bluer, but you get much more detail about the political inclinations across the country. But that map is actually hard to see big differences in, because in reality, there are very few places where you're going to get a total landslide, where nobody is going to vote for one of the candidates. So we could adjust our colors so that once you hit 70% for one candidate, you max out the color scheme. And so that's what we've got on this last map. So that highlights some of the redder areas, because if you've got 70% of the vote for McCain, you're essentially a lock-in Republican county. And then likewise, if you've got 70% for Obama. So this last map gives us a lot more detail about the political inclinations in different parts of the country than we got from that first map, where we had a lot less detail, where we had only 2 colors and we were doing it at the state level. Now the catch is, when you look at these different maps, in a sense, that first map is still the best map, because that first map is the one that tells you who actually won the election, since the election is based on the Electoral College, which is a winner-takes-all at the state level type of system. So Obama got all of the electoral votes for Pennsylvania, even though, as we can see from those other maps, there are large areas of the state that preferred McCain, and then vice versa for some of the states that McCain got all of the electoral votes for, even though there were substantial areas that preferred Obama. So the choice of how to represent this data, what area units to use, and how to break them down into different colors matters a great deal and depends on the purpose that your map is serving. So let's take a look at some of the different category systems that we can use to divide our data up into different colors. Generally, we're going to want to take a whole range of data that can have numerical values across a wide scope, and we want to break it down into just a few different colors to make the map easier to read. So one way that we can do that is what's called the equal interval system. In this case, we take the range between the lowest value, so in this case this is average household income for different counties in Pennsylvania. We're going to use this as an ongoing example of these different category systems. You take your lowest value, so your value for the poorest county, you take your highest value, the value for the richest county, and you divide that into equal ranges. So the width of each range, the difference between the richest county that could get that color and the poorest county that could get that color, is equal for each color. And so what you see on this map is there are only a few counties that get that highest color, and then there are a lot more counties that get some of the lower colors. We have kind of a skewed distribution with just a few really rich counties and a lot more counties towards the middle or bottom in terms of their income. Another system that we could use is the quantile system. In this system, we want to make each color have the same number of area units. So in this case, the same number of counties will be colored in each color. So if you were to count up the number of counties that have the darkest green, that would be the same as the number of counties that have the next darkest green and the next darkest, etc. And since in Pennsylvania, the counties are roughly similar in size, we don't have any super enormous counties or any super tiny counties, that means you'll see about the same amount of each color on the map. So in this case, you see a lot more of those darkest colors than you saw on the equal interval map because of how the data is distributed in this case. And you look at the number line at the bottom there, you'll see that the width of those categories is very different. You can see that if you look at the numbers on the legend next to the map as well. That top category, that darkest color, represents a much wider range of possible numerical values than do some of the other colors. Because we're just going to start from the top, count the top, in this case, fifth of the counties, because we got 5 different colors, color them one county, one color, continue on the next fifth on down, gets the next color, the next fifth on down gets the next color, etc. Another system that we might use is what's called the natural breaks system. In this case, what we do is we look at our number line, we look at the distribution of values, and we look for spaces where there's a gap, where there's a spot where there aren't any area units with a value in that range. So in this case, if we look starting from the top, between the third and fourth county in terms of rank by income, we see a nice big gap there. There are no counties with incomes that fall within that range. So that's a natural break in the data. And so we can put the break between our different colors there. The advantage of the natural break system is that each color represents a cluster of counties that are similar to each other and different from the ones of the other colors. Any of those other systems might drop that break right between two counties that have almost exactly the same value. One's just a few dollars richer than the other, but that's where that break happens to fall based on either making the categories of equal width in an equal interval system or of putting the same number of counties in each category in the quantile system. So all of these category systems are equally valid. All of these category systems take the same data and accurately represent it on the map. So which category system you're using is a matter of choice. What do you want to emphasize about your data? It's the same underlying data in all these cases. It's being accurately represented, but you can see how different of an impression you get from different maps. The equal interval map, for example, creates a much starker representation of economic inequality. You got just a few very rich counties and a ton of very poor ones. It communicates that sense of severe economic inequality, but at the expense of very little differentiation between the poorer counties. It's hard to see through most of the middle of the state which counties are richer or which are poor because they all end up in the same categories. When we go into the quantile system, in this particular case, it gives us more of that detail in the central areas of the map, but without creating that impression of a stark economic contrast between the rich suburbs of Philly and the rest of the state. In this case, the natural breaks map is somewhere in between. Now, those different impressions are artifacts of the distribution of data that we have. The fact that when you look at the data on populations of the counties, you get just a few very rich ones and a lot of poor ones. If your data was distributed differently, if you had data where you had a lot of area units near the top and fewer near the bottom, you get a different look to your map when you mapped it under these different Choropleth category systems.